So I have some questions about entanglement.
Mm-hmm.
Before we get to that, can you outline what entanglement is?
Yes. Entanglement is tricky to explain depending on the level. I was recently doing that for really young people, and I was like, oh my God, I have to think about this a little better.
So there are two classes of audiences that watch this.
Mm-hmm.
One are researchers, professors, postdocs, PhDs, and so forth.
Yeah.
And then another is lay people, artists and gamers and what have you.
Yes.
So you can address it to both audiences. You can say, okay, the level one explanation is so and so, and the level 2 is this and that.
Okay, let me go first to physicists. I find it easier to explain, and then I'll see what I say in the other case, because this is improvised. No, I'm just haven't thought about it. So in quantum mechanics, you say that the state of a system, let's say one system, so let's think about a spin half particle, can be in a superposition of up and down. No, so this is a wave function. This is, again, we're not going to interpretations of is a particle really up and down at the same time. Let's just keep it as the state of the system is given by a vector in the Hilbert space. So I would say that is like the first postulate of quantum mechanics. But then you want in quantum mechanics to describe what happens if you're now describing two particles or two systems, not just one. So we say that it's a bipartite system. So the way that you do that in quantum mechanics is a special mathematical way called the tensor product. So you take the Hilbert space for this system where your state is the vector in the Hilbert space, and now you add a second system. So the total Hilbert space is the tensor product space of the two. And then in this bigger Hilbert space, you also have a bunch of possible states. And if you look at the states, there are some special states in which you cannot write the state in what we call a separable state. So a separable state would be this particle is in, let's say, some superposition, tensor product, this one. So these states, physically, let's say, you can produce by local operations and classical communications.
I love this.
Yes. So let's think about Alice and Bob preparing quantum states, so of a bipartite system. So let's stick to the spin example and so on. So let's say that Alice is in her lab and Bob is in his lab. So then local operations means Alice and Bob separately in their lab are allowed to do whatever they want to their state. So they can rotate it, they can do a quantum gate on it, they can even measure it. And then classical communication means, they use a photon to send information. They talk on the phone. Alice says, I'm going to measure in the Z direction, and any kind of things that they want to agree on the phone, that's classical communication. So if they take their spin particles, each one has their spin particle, and they only do local operations and classical communications, the states will always be separable. Now, there's another type of states that are like the entangled states, and those cannot be produced by only local operations and classical communication. They need some interaction. So the interaction could be bring the two spin particles together and then do like a spin-spin interaction. And then you produce like a global state. And we talk more about what entanglement is in a moment. But before, you could also entangle them by having Alice get her state entangled with, say, a photon. So a third system, but a photon is a good example. Then you send the photon to Bob's lab, and the photon interacts with his spin particle or his system, and then these two become entangled. But they require some interaction. So this means a global, not a local operation, and so on. So what's special about entangled states is that they're very highly correlated. So more than any classical correlations that you could create. So the classical correlations would be Alice and Bob talking and say, okay, look, if my state is up, yours is up too. And my state is pointing down, yours is too. And they could agree on any number of combinations of that, and that is all classical correlations. But what happens with entanglement is, well, on one hand, if you make a measurement in Alice part of entangled pair, the state of Bob will be sort of immediately take a certain state. No? So the states of Alice, so in Alice's points of view, her state is in a superposition of up and down. So she doesn't really know what state her system is. It's not just that she doesn't know. It's indeterminate until she measured, because it's in a superposition until she measures. And Bob's state, the same thing. But if they're not entangled, if they do this experiment many times, the outcomes will be not correlated. But if they're entangled, let's say if it's maximal entangled, like a Bell state, they will be completely correlated. So every time that Alice makes a measurement, then that will determine Alice's state, and that immediately gives Bob like a given outcome. So in that sense, what Alice does in her lab affects the outcome of the states in Bob's lab. And that's very different to what happens classically. That never happens classically.
Just a moment. Before we get to the explanation for the lay people, the people who aren't physicists or aren't mathematicians, it's said that the correlations are in quantum entanglement are stronger than can be classically. Okay. But then in the example that you gave where I usually say Angelina and Brad instead of Alice and Bob. So Angelina, she says, look, I have a spin down, and Brad says, I have a spin down as well. And then it's usually the opposites in the real world, but doesn't matter. Can't you just have a coin? A coin is, if you see that it's heads, the opposite is tails, that's a 100% correlation. And so how can you ever beat a 100% correlation? What does that mean? Give an intuition to that.
Yeah, okay. So the intuition, I think I would say, is like, if you think again about a spin half particle, you could measure the state in different bases. So let's think about this example. We were talking of spin particle in a magnetic field. So the state could be pointing up or pointing down, or in a superposition of up and down. But if I measure in that direction, in the set direction, what will happen is that I will find either the state up or the state down. But in quantum mechanics, you can choose a different angle. So let's go to the set plane. So let's say if the state was here pointing up, when you measure in that direction, it's also going to be 50-50, either, like pointing this way or pointing the other way around. So take another angle, like at 45. So if you take there, it's also going to have a probability of being pointing in that direction or in the opposite direction in that angle, right? So when you have an entangled state, you will always find perfect correlations. Okay, so the coins are perfectly correlated in one instance, right? In the heads or tails. And that's it. That's the only thing you have. But in this quantum example that we're talking about, you can make measurements in how many bases?
I see.
An infinite number, because you have in the sphere, you have an infinite number of possible angles, right? So so that means that you could choose among an infinite number of possible bases, and the state would always be correlated.
So the amount of questions you can ask the coin is just, are you heads or are you tails? Whereas the amount of questions you can ask the quantum system is infinite.
Yeah. So if you would say, but Alice and Bob cheated and they agreed on, they shared this information, well, they would have to, in principle, share an infinite amount of information in order for you to see that sort of outcome.
Great.
Yeah.
Okay, now explain entanglement.
Okay, I explain
the ELI5 version.
No, I don't know. I mean, I think the intermediate one is like really hard.
How about the 15-year-old then?
Yeah, I tried to explain it to children. It's like really,
forget about children. Children are watching this.
13-year-old. I meant it's hard, But what I used was a Bertelsmann socks. Do you know about Bertelsmann socks?
Bertelsmann socks.
Yes.
No, so I know about socks.
John Bell.
Yes.
Had a student who still lives in Vienna. Reinhold Bertelmann, he's a wonderful professor. But John used his student, his PhD student at the time, as an example to teach people what our classical correlations are, because every time you look at his feet, that he wears one green sock on one foot and then a red one on the other. So like he would use this example to measure, to see, what correlations are. And actually what's really nice about Reinhold, that, he's still in Vienna, is that if you find him in the supermarket, you will still see that he always wears one green sock in one foot and the red one in the other one. So I think that is like a good way to explain what classical correlations are. And then I was kind of trying, I had very little time. And I had to and then I was trying to explain how would the quantum version of the socks work. And it's a bit like you're wearing these socks that are undetermined, right? They're red and green at the same time. But now you need two people playing socks, so somebody has red and the other ones have green. This is kind of the child explanation, but for audience that are adults, I mean, it's like a little bit too simple, maybe. It doesn't really make much sense to explain it with socks, I think. But I think that the lesson is that the correlations are stronger than the classical correlations. So I think the coin example is very good. You would say, well, you can create classical correlations by, I don't know, producing some sort of outcome in which you always get the same outcome, and you, like in the example of the socks, you could agree on something so that when you make the measurement, you find the same result. But quantum correlations are much stronger than that. I think the spin half example that I did, I think this is probably not too bad for the other audience, no? Or you think it is a bit...
No, it's perfect.
No?
Okay, theoretically speaking now, what do we know about entanglement in a relativistic setting? And then we can get to the experimental side after.
Yeah, so that's how I started thinking about, let's say, quantum mechanics and its connection with relativity, because when I learned about entanglement as a undergraduate student, my teacher said, okay, you have these spin half particles, you bring them in contact, you entangle them, Alice takes her qubit and Bob takes his part of the state, and then they use them to do teleportation. But nothing mathematically, theoretically happened to the state. There was a Bell state, and I was just told, okay, now Alice and Bob separate. And for me, that made no sense. I was thinking well, but what happens if they're doing that in the presence of a gravitational field, if the space-time is curved, if they're moving close to the speed of light? What happens? The entanglement is always the same. That doesn't change. And I became interested in that question.
Quick question about your question. Why would you expect it to change?
Well, I mean, because you have in relativity that often things depend on the state of motion of the observer, right? So clocks change, the ticking of the clock depends on the state of motion of the person carrying the clock, or you also lengths and so on. So for me, it was kind of quite obvious that, we needed to either show theoretically that is conserved under all circumstances, or it's not. So I was curious, and I wanted to know how could I study that. But then, I mean, I kind of forgot that I was worried about for that some time, and I just learned about entanglement and so on. But then I became a postdoc at the Perimeter Institute. I think I told you that story before. And then what happened is that my friends were working on gravity, and I became sort of very jealous of that. And I thought, oh, I want to learn more. And I thought, well, I've already changed fields a few times. So I thought maybe it's not a good idea that I change fields yet another time. I had some nice papers already in quantum information. And I started to sort of merge things. So I started to think about what happens. How can I think about entanglement in relativistic settings? And that's how I started to learn, because I didn't know it before, quantum field theory in curved space-time. And the first paper that I wrote on that direction is called Alice Falls into a Black Hole. So it's like entanglement in non-relativistic, in non-inertial frames, because some colleagues had looked at what happens to entanglement, sort of if you change the state, but everything inertial from the perspective of different inertial observers. And then I thought it would be interesting to find out what happened with the description of entanglement from the perspective of different non-inertial observers. And that I found like a result that for me at the time was surprising, because I thought that entanglement was like a property of the system. No, so you have these spin particles like we were just discussing, and they are entangled to some degree, maximally entangled if you want. But in quantum mechanics, it's like clocks always tick at the same rate. The underpinning transformations are Galilean transformations. So entanglement is sort of a conserve, or we don't even think about what happens from entanglement in a different perspective, because that's more like a question from relativity. So I was interested in finding out then what would happen. And what I found out is that the degree of entanglement in the system dependent on the description of the different observers. So later on with Paul Alsing, I wrote a review called like Entanglement, Observer-Dependent Entanglement. And at the time, it was for me surprising, the connection. But that is how I started to work in the interplay of quantum mechanics and relativity, asking questions about entanglement. And for example, another thing we did, and that was with Frederick Schiller. We looked at if you have a state that is separable, let's say in the past infinity, and then you have a period of expansion. We did toy models, really, like the Robertson-Walker universe and so on. What happens to like the state in the future? And we found that, the expansion of the universe would produce entanglement between particles created by the expansion. But these were all very toy model questions. I mean, the universe doesn't even behave like a Robertson-Walker universe. We know that. But we were learning how to think about entanglement in sort of relativistic settings. And you had to be careful with things like particle create, like different in curved space, like different observers don't agree on the particle content of the field. So how do you think about entanglement in that case? In quantum information, what you need to talk about entanglement is to make a bipartition. So maybe you have many particles, like spin particles, but you say, okay, the left side is system 1 and the right side is system 2. And I look at entanglement between these spins and that spins. But you can also make a different bipartition and say, like, all the spins looking up versus all the spins looking down. How entangled are they? And then that's a different bipartition. But you need to give me the bipartition and then you calculate the entanglement. But in curved space, different inertial observers completely disagree. So this notion of subsystem was like, I started to learn how difficult it was becoming to describe. So that was one of the first kind of problems that we found with studying entanglement in relativistic settings.
Hi, everyone. Hope you're enjoying today's episode. If you're hungry for deeper dives into physics, AI, consciousness, philosophy, along with my personal reflections, you'll find it all on my Substack, Subscribers get first access to new episodes, new posts as well, behind-the-scenes insights, and the chance to be a part of a thriving community of like-minded pilgrimers. By joining, you'll directly be supporting my work and helping keep these conversations at the cutting edge. So click the link on screen here, hit subscribe, and let's keep pushing the boundaries of knowledge together. Thank you and enjoy the show. Just so you know, if you're listening, it's CurtJaimungal.org, CurtJaimungal.org.